timing analysis. And just before we do that, I just want to welcome everybody back. It's been a while since we've done anything face-to-face in terms of our regular meetings. Would like to thank a couple people. First of all, Rochester Public Schools for letting us come in and do this. It's kind of hard to find venues right now that'll let us bring in food, so that's great. I want to thank some members of the board, because Chris White, our vice chair, he did all the work working with the facilities from RPS to set this up. Lena, our secretary, sends out the notices and keeps track of the responses and that. And of course, Jonathan here with the technology. And I will tell you, going to some of these regional meetings, we are ahead, way ahead in terms of how we can simulcast and remote broadcast and record and all of that. There's a lot of bigger sections that don't do anywhere close to what we're doing with that. And we've been doing that for a while, so that's great. One other thing about the location, one of the reasons we're here is some of the COVID restrictions coming out of the pandemic with Mayo Clinic. But also we'd like to just kind of branch out a little bit into the community and have a few more options in terms of where we have some of these meetings. So we're still kind of experimenting with that. We've done this here one other time, but we're going to continue to look for, different venues and try to move around a little bit more than we have in the past. Although we may end up doing a lot of stuff at Mann Hall too at some point again as well. So with that, I think we'll move into the technical presentation, and I'd like to introduce Tim Helvey, who's from Marvell, and he's going to talk about static timing analysis, one of his principal areas of expertise. But Tim is a principal engineer and technical manager at Marvell, where he leads the ASIC timing analysis community. He has 20 years of experience, including some time at IBM and Global Foundries. He has multiple patents related to timing analysis and timing closure. And he has his engineering degrees from Purdue University and the University of Minnesota. In his free time, he enjoys travel and cycling. And with that, please welcome Tim Helvey.
Thank you. Thank you for the introduction. So my talk today is computational trends in silicon sign-off, or you're going to need a bigger boat. And great introduction, thank you. So I will skip that slide. Quick overview of what I want to talk about here. I'll try to stay pretty high level and not get down into the technicals of static timing analysis. But if you have any questions there, yeah, we can do that too. So in our field, custom silicon development continues to evolve. It remains an exciting field, but with each generation, development becomes more complex and more expensive. And yet people are still hungry for newer things, more data, more 5G, more AI, more machine learning. So we keep making it work, but it becomes more challenging with each new chip that we put out. So this talk will explore one specific area of silicon sign-off and the effects on the usage of our computational capacity. So diving into static timing analysis, essentially it's a graph architecture. Very grossly simplify it into just have a few boxes in the design, and we're trying to calculate when signals are arriving at each of those points in the design, and each box on the graph has a delay associated with it, and we need to calculate how the signals are arriving at each box. It's relatively simple algorithm. Most of the work can be threaded well into 16 and 32 threads. But there's always some part of the flow, maybe user scripts or other parts of the tool flow that still run single-threaded. So take a look back in history. Not quite to the beginning of my career, but as far back as I could remember in my career, about 15 years ago, we were looking at chips that had 1 million to 10 million objects. So as I was saying, calculating the arrival times in each of those boxes, we'd have 10 million data structures that we need to keep track of. And in terms of how we designed our products, 15 years ago, we were starting this shift from where we would generally work on the whole chip as a single data model to where we started looking at hierarchical data models, calling it physical hierarchy. So we'd build one unit in the processor, and then from that building block, build up a processor with 10 CPU units, etc. At that point, maybe we had a machine pool. If you knew where to look, there might be 10 machines that had about 64 gigs of memory on them, and some of our sign-off tasks would need that full capacity, 10 machines, 64 gig. And back then we thought, wow, these are big machines. So fast forward to today, over a span of 15 years, I plotted it out there on two different scales. The increasing data volume with the blue bars, and then the decrease. I used memory cost per gigabyte in this example. So over that 15-year time frame, our compute resource has gotten better and cheaper. Memory price has dropped about 80%. Processor single thread speed has doubled. But over that span, our designs are now bigger by a factor of 150x. So we've vastly outpaced the ability of our compute resource to keep up with the size of our designs. Additionally, our designs have become more complex, different power states, different performance modes that they may support in one product, and more complex, more accurate models, also adding to the computational demand. So I put the key question down there, and I'll say right up front, I don't have all the answers. This is the constant question. How do we handle a exponential increase in data volume? But with this background, I'll go through some of the challenges and some of the things we've learned along the way that I think are general trends. Any segment that's focusing on large data, computation of large structures, is probably running into some of the similar themes. So first off, easy. We can buy bigger compute servers. Just keep asking for more memory, and this is part of what we do. Of course, this isn't the price of a server out in data center, but I went on to Dell.com, and how much would it cost to buy my own 2 terabyte server? It's about $100,000 when you scale up to having 2 terabytes of RAM in your system. So let's say for a big design, I need a 2 terabyte server just to run one analysis, and I need to do 40 of those in parallel. So now I'm talking, I need $4 million of compute capacity just for my task. We're starting to attract maybe some unwanted attention at how much our compute activity is affecting the bottom line here. Let's look at CPUs also. Modern processors have more and more threads, so easy. We'll take more of those threads, but we see diminishing returns. Most of the algorithm can take advantage of threads up to 32, even 64 threads, but there are still parts. The single-threaded parts begin to dominate, or not even single-threaded, but some parts get gated, waiting on the other threads to do their thing. So there's diminishing returns there, but we have over the years, we've gone from 4 to 16, 32, even 64 threads for some things we do. Realities of the software model that we're in. Sometimes when we turn up the threads to 32 or 64 threads, now we're paying additional licensing costs for those higher thread counts. So let's get smarter. Let's spread it across multiple machines. So our software tools support, call it super threading or automatic partitioning to distribute the workload across multiple clients. Now in this architecture, we have a master and several clients that are doing the compute work. Some parts of the tool flow are on the master, still bottlenecked a bit there, maybe even single-threaded on the master. But other parts of the flow can scale out well on 20 clients. So 20 clients, now we're using 640 threads, much more computational capacity than we had on a single machine. But this gets into some new types of IT concerns. So it used to be a simple task to just submit my one job to the machine pool. The load management system would assign a machine, and I wouldn't have to care very much about that process as long as it found a machine. And if it didn't find a machine, that's somebody else's job to figure that out. Now we have to pay more attention and go back to what I said a couple slides ago. If my workload costs $4 million, I better be doing everything I can to make sure that I'm using that $4 million efficiently. So with traditional single machine approach, we have little control over the memory footprint. But now I can choose, do I want to have 6 clients that are of a certain size, or 8 clients? Some of there's more overhead if I scale out to 8 clients, but it may be that 8 clients fits better in my available machines, and I tried to illustrate that on the right there. With 6 clients, I only needed 6 machines, but I'm wasting about a third of the resource available on each of those machines just by the way I've split up my data model. And so I may actually be more efficient if I split to 8 clients, and I can pack that into 4 machines now instead of needing 6 machines for my workload. And I can do that exercise once, and then I'll realize that I have a machine pool that has some machines with 350 gig and some other machines with 256 gig. And now I have to repeat this exercise for my heterogeneous machine pool, trying to map everything into optimal usage of the available machines. Now my cost equation gets more complicated too. If I have a single machine, there is overhead to this process where we're distributing the workload across multiple machines. So on the single machine, perhaps I can run for 12 hours. If I do the math there, CPU times time, 16 CPUs times 12 hours, 192 CPU hours. My distributed algorithm is, as shown here, 320 CPU hours, much less efficient. If I'm paying per CPU hour, perhaps I want to use the STA, the single host algorithm. But if I'm paying per, if memory is my bottleneck, in this example, now I'm using more memory, but I can get it done much faster. I get it done in 5 hours. I had almost somewhere around 40% more memory was required, but I get it done faster. So it's roughly a 25% reduction in the memory cost for that workload. Here's a fun one. So ideally, we submit our job to the pool, it finishes, and we get our results. And that's true maybe 97, 98% of the time. sometimes things happen to the machine, or the something glitched in the network or the file server, or somebody else put a workload that was poorly estimated on the same server, and the I/O got overloaded or memory got overloaded, CPU. For whatever reason, our job didn't complete properly. If I'm using one machine, let's say I have a 97% success rate on one machine, now I go with a master and 3 clients. Now my same conditions, my success rate has gone down to 89%. If I use a master with 20 clients, now my success rate has gone down to 53%, which is really unacceptable. I probably, my example is a little artificial here. Starting with 97% isn't quite true, but I do expect that I'm going to have some concerns with this failure rate scaling up to 20 clients. And some of this is state of where the software is. Of course, more mature software, we may be able to recover from a client going away, spawn a new client to replace that one. But state of the art today for this algorithm, if one client dies, the whole job is lost. Waiting in the queue. Again, a question of balancing the expense, the impact on other users of the queue. Ideally, I would have, so I need 20 machines to run on. Ideally, they would all be, ideally from my end, not from the guy paying for the machines, but from my end, ideally those machines are all sitting there idle. And as soon as I submit to them, or as soon as I submit to the queue, hosts get assigned and my job starts. That's not a good usage of the queue for all the time that those machines were sitting idle. So ideally, we're getting other workload to get in there, and now I have to wait. I have to wait till all the clients are available. And with this master client approach, now I need 20 machines to all become available. And in realities of the queue, that may be hours before somebody else's job finishes, and I can get all my 20 hosts to start. So we've got to make some balance there between having reserved machines just waiting for our jobs, or having the delay waiting for the queue to become available. Very similar illustration here on CPU idleness. So in this model, the 4 rows here, the first row is the master, and then in this example I gave 3 clients. So when I first submit my job, the master has to read in some data models, read in a description of the design I'm working on, find how to partition that, and split it out to the clients. And so, say for the first 4 hours, my master is busy, and my clients aren't really, they're doing some little tasks, but they're mostly idle. And then my master kicks off the clients to do the analysis, and now my master is idle. Maybe my master is idle for 10 hours, and at some point in there, the first client finishes their workload. And now they're idle. Maybe they're idle for a couple hours while they wait for the last client to to finish that task. And then we're back to the master has some piece of work to do, and then we're back to the clients again for the next step in the analysis. And if this is all on one machine, nobody notices. If it's distributed on several machines, if your IT department is paying attention, they're going to point to that. They're going to say, okay, you checked out one of these expensive machines. It's got a terabyte of memory, a bunch of processor threads. and for 12 hours you didn't do anything. So justify why did I give you high priority expensive machines when you're just going to sit there and do nothing with them? And so then it's my job to just say, yes, I know what I'm doing. And that's limitations of the current software. It would be nice if the master could do some of that processing that the clients can do, so it's not completely idle. But the point on the master is to try to keep that memory footprint as low as possible. And the clients are doing the compute piece, and the master is trying to in this model, the master is usually around a terabyte of memory for the data that it's responsible for, and the clients are around 256 gig to 500 gigs of data that they need to handle. So that's one piece that catches some attention. We've been cloud computing has been hot item almost as long as I can remember. I guess we've been talking about it probably nearly 10 years, and it's been getting traction for a good portion of that time. So it should solve all of our issues, right? And it does solve some of our issues and creates new issues. We can go into, for example, I'll refer to one provider here. We can go into AWS. We can get some on-demand instances, and I wait 15 minutes, and now I have all the machines spooled up. They get the operating system loaded, and I can submit my job to those. Great. So now I can easily address the peaks and valleys of my IT demand, with a catch that I'm just newly learning some of the cost structures of the cloud computing. So in the environment we're working in, we can have dedicated instances that are billed at one rate, and on-demand instances that cost roughly twice as much as the permanent instances. So now I'm not just doing my normal job. I have to try to predict how many of those permanent instances do I want, and how many of the on-demand instances do I want. And I also, I can't get too carried away. If I say, give me an unlimited number of on-demand instances, well, somebody's going to run a workload that suddenly needs 10x of what we forecasted, and we need to rein that in as well. So now we're paying a lot more attention, not just to what will be our peak, but what's our average, and how do we want to handle the peak, and rebalancing. The ability to rebalance every month is, it's a blessing and a curse. I can scale up quickly, but I also need to every month or so reevaluate that projection that we've given. There's another aspect in the cloud. We're not taking advantage of it for this workload, but there are so-called spot instances that are low priority. I think they can even, your job can get dumped off of them if something else, essentially someone that paid more, comes along and interrupts your job. But periods of low demand, you can pick up these spot instances for short jobs that you can afford to lose. So everything I've said so far assumes that we are doing this task on our full product as one monolithic task. Of course, I said we can partition it onto multiple machines, but I'm still treating it as one data model, just auto-partitioned. So what we have to embrace now is the hierarchical approach here, breaking up the data model. my traditional approach. Don't really like the way I chopped up this slide here, but the traditional approach is easy. I just have a flat design and I analyze my full design. Now I'm proposing a hierarchical approach. And so I have a level 1 that I analyze, and I create some abstracted model of level 1. And then I work at level 2. Visually, this greenish box over here. I work at level 2, and I have some information about the level 1. And then once I'm done with level 2, I again create an abstract of that level, and now I analyze the topmost logical layer of my design. And then I have to prove that what I did at the lower levels was accurate. So in this model, we're creating something we call a context. And so context is just like a reverse abstract. It tells us some information about the upper level that the lower level needs to know in order to accurately do its analysis. So as I've gone through this, the key point here really is I took something that was a big, large workload, but it's a single step and it's easy for me to kick off. Now I have 5 steps in my flow and they're all smaller steps. So call it work smarter, but also work harder. So the first example there at the top, in the flat architecture, I can use some parallel computing on multiple hosts. Let's say I can get my turnaround time down to 12 to 24 hours, somewhere in that range. Now with this hierarchical approach, of course, there's a little more variation here. I just took a very simple example. I said steps 1 through 5 all take 6 hours each. Now, great, I took something that was 12 to 24 hours, and now it's 30 hours. That's worse, right? Well, in some ways it is worse. But with this now, I've broken it up into smaller pieces that all have a smaller footprint. And some of our typical architectures have a lot of reused parts of the design. So let's just say you've got a processor with 100 cores. Maybe I only have to analyze that core one time. I can create an abstract of that. And then instead of doing my full flat analysis with 100 redundant analysis of the core, analyze the core once, and then I need to analyze the boundaries of that along with the surrounding layer of architecture. So longer turnaround, but smaller footprint, hopefully a much smaller IT cost. But as a user, I would much rather do the first one. I can kick that off, I can go home, I can sleep, I can come back in the morning, hopefully it's done. Hopefully I didn't run into one of the failed jobs along the way. But now, when I staff my teams, I'm taking what was kind of a push button thing before, and now it's like 25% of somebody's time is just managing all these steps in the flow and the abstract models, making sure that they all got written correctly and consumed correctly. More workload, but hopefully I've cut down on some of that $4 million IT cost that I set up at the beginning. In some ways it's saving money, but it's also awfully hard to find good skilled engineers these days too. So different trading off different challenges. But there's a huge benefit here that I haven't touched on yet, and I think that's I tried to illustrate that on the right with the 5 little blocks there with the arrows under them. With the flat architecture, I can get 12 to 24 hours turnaround, and I have the full answer. With the hierarchical architecture, any one of those steps I could iterate on in 6 hours. So if I run the first step and I see that unit has some violations that I need to go work on, I can keep iterating in 6-hour turns instead of the 12 to 24-hour, get that as clean as it can be, and then proceed on to the next step. So this breaking it up this way, the modularity is a big benefit. Until I get down to the very end of the project, and I really do need to run through all of the steps to get the chip out the door. Lower risk too, because I'm not, if I run into something that fails, I'm not losing a 24-hour job. I'm only losing a 6-hour segment of the workload. So conclusion here, the computational workload associated with our silicon sign-off is growing exponentially at a faster rate than improvements in compute hardware. The software and the design architectures give us options to adapt to available compute hardware. Of course, with all of those new advancements, we have more work for the team to do and new techniques and tricks to learn, but that keeps it fun and interesting, and keeps us all employed and able to go on to the next technology generation. The cloud facilitates our hunger for compute, but at what expense? There's overheads there and additional complexity we have to deal with, but I expect it to be a reality for our peaks and valleys in our compute demand. And I think that ends my talk here. So I am wide open for questions and answers at this point. Yeah.
A long time ago, you would just submit a job to the queue and it would run and that was it. But now you have to do all this extra management. How much overhead do you think you've gained over time now having to manage the whole process?
Good question. It's the amount of overhead that we've picked up along the way. I'll give the very short answer. I think 20 to 25% workload overhead. The trend here too, of course, is that our chips are bigger and bigger, and where we may have had 15 years ago, our chip would just be one unit that we would work on as a whole, and now I might have a chip that has been broken into 100 different subunits, and we're building up pieces from those. And so the designs becoming more complex by themselves have grown my teams substantially. But this specific aspect of just trying to manage the sign-off process. I'll take an example. I have one of my teams that has about 8 people staffed on the team, and one of those people is spending half their time just kind of dealing with issues associated with the workload that I talked about here. And I've got another person that's probably spending 25% of their time as well, with a different approach to the same problem. Yeah.
So is the sign-off workload predominantly computational, or is there some other memory bound or storage bound or network bound?
Yeah. What are we bound by? I would say it's primarily, at least in terms of available compute resources, it's primarily the memory. If I take my biggest design and I try to run it on one machine, I probably need 2 to 3 terabytes of physical memory on that machine. And I would use 32 of the processors. There'd be probably more threads than that available on the machine. As I scale out to this distributed architecture, My clients, I'm probably even more memory bound in that case. I'm trying to fit it into 512 gigabyte clients. That's a sweet spot for the cost of those clients. But I'm, again, going to use 12, 16, maybe 24 threads, and there's probably additional thread capacity there that I'm just not using. Partially because of diminishing returns, and partially that at 16 threads, there's a license increment there that discourages me due to the diminishing returns. Yeah.
I understand like the theory of why the hierarchical method is better than the flat method, but I'm confused on what like software components or other technical aspects you would need in order to move from the flat to hierarchical.
Yeah. I'll get real specific here, and then we can build on that. In this specific workload, there's two major tool providers in the industry. It's Cadence and Synopsys, and they both provide static timing analysis tools. And so within the tools provided by those vendors, these techniques are all, break it down to its simplest terms, I just need to add a few additional commands into my tool flow, and it will spawn the job off onto a child process on another machine. I went partially down the wrong thread there. That's where we're automatically partitioning things. When I go with the hierarchical process, using the same tools, and it's all models that are built into the tool. So from my vendor provided static timing analysis tool, I will write an abstract model that it's essentially taking out all of the storage elements internal to that design and just leaving the outermost storage elements that communicate with the periphery, and then the next level up will consume that. So it's that abstract. We like to see somewhere between 90 and 95% reduction in the model content there when we're using the abstract. Some cases, if there's a lot of logic packed into the periphery, we're not going to see as good of reduction, but generally it's around 90%. So then I have, getting into some more of the challenges there, if I have a design that has 100 units on it, do I want to go through the steps of creating 100 abstracts, an abstract for every piece of the design, where some of the pieces are really small, and maybe creating an abstract for it doesn't benefit me that much. So I need to evaluate where's the greatest potential, where do my returns start to diminish, start with the biggest pieces in the design, abstract those. And what I'm really trying to get in my current architecture, if I can use those abstracts and avoid the distributed master client model that I talked about, there are, I don't want to go down both of those paths at the same time, the master client architecture and the hierarchical architecture. I can, but if I can use the hierarchy to get me away from the other technique, there are significant advantages to that. Yeah.
That like somebody could do independently, like with AWS, or is the other software that you mentioned, the Cadence or Synopsys, only something that you would have access to if you were already part of a company like Roper?
Yeah, great question. So this is very, the techniques are general and show up, but not that there's other workloads I can think of within getting a chip out the door where the same technique shows up. The specifics of it are very specific to the tools that we're using. There's nothing there that is, I don't think our tools have anything that's really conscious of AWS. It's just machines that are available, and it's our tools, at least at this layer, don't really care whose machines they are and how you got them. It just needs to start a process on a machine. And then there is another layer that's responsible for the queue management and getting the machines to us. Yeah. Let's see. I know this guy, so I'm going to take this question. Oh, yeah.
So kind of following that, would you say this is particularly challenging for timing, or are there other disciplines that spend much time thinking about this as you do?
See, I didn't recognize this guy with the hat on, so. Sorry, now I joked and I lost your question. Say it again.
Would you say this is particularly challenging for timing, or are there other disciplines that think about it as much as you do?
The next one that comes to mind is the power supply integrity. There's pieces of that analysis where we're in my world, we like to think that you put a power supply into the chip, the whole chip runs at 750 millivolts, it's nice and uniform, but we've got parts of the chip that are switching faster than other parts of the chip. Dynamically, voltage is changing with every picosecond, and so the power supply analysis has to do some of that with a full chip view of what the power distribution network looks like. And some of these techniques are starting to enter into that landscape. There's trying to think where else does this show up? In physical sign-off, yeah, just shapes verification. That's a very large problem that has been multi-threaded to death, and very well multi-threaded, but that's another one of the very large workloads. On the other hand, the physical design, the layout of the objects, all these little AND gates, OR gates, the layout of that, like I said, back around 15 years ago was when we started integrating some hierarchical models, and the physical design was really the first piece to, at least the first piece that I get exposed to jump on that bandwagon, and we started having some physical hierarchy. We were still timing, doing the timing analysis and several other parts of the flow with the full model, but placing the objects in a hierarchical fashion.
We're having trouble with guys. Dave?
Oh, okay.
Not you, Dave, other Dave. I thought he was like the only one online. Anyway, do you think there's too much reliance on humans getting in the way of dividing up these large designs for master client assignment?
Too much reliance on humans getting in the, I would
we
love,
break up the design and tell the machine, here's how I want the design broken, where maybe I want more algorithm development there
yes.
to figure that out.
Yes, I think that two ways of looking at this. First is, I showed that chart where over the past 15 years, we've our data volume has gone up 150x. So right now we're looking at, I'm not sure what our transistor counts are at, but at the level I look at it with the logic gates, we're up to 1.5 billion. We're working on a design in that 1 to 2 billion range. There are other, being in the top 10 here is not really an honor that you want to have, because it means your design is really giving you challenges, but we're up there. Maybe we're in the top 5. There's other groups looking at like 2 billion instance. That's kind of where we're at right now. But so we follow that trend. Say we're looking at 3 nanometer, and then the next node, we're going to be at 10 billion in a couple years. And, you know, there's constantly thought that one day we're going to hit a wall of technology, and you know, we just keep going right through that wall every generation. 10 billion instances, 100 billion instances. There's no option except that the software tool vendors have to get better at this, and they're getting there, not as quickly as we'd like them to be. But at least there's at least we're not stuck on one. There's two players playing against each other, Synopsys and Cadence. But I think it just has to get better for us to be able to continue this and not have, you know, one or two people full time on the team that are just dealing with what does our footprint look like. And I think there's some pieces here that some of it can be automated. Some of it really is, it's not that hard to figure out some of the pieces. I mean, I can go look at my design and I can figure out what's the biggest unit, and it makes sense to abstract that first. And then what's the second biggest? Okay, I'll go abstract that next. Within the current architecture, I think there's it's extra work, but it's not necessarily hard work to figure out some of these pieces. So I'm not really looking for a tool to tell me which pieces to abstract. I'm looking for a model that makes it so I don't have to abstract, or that's just completely hidden from me. But with the current hierarchical model, I don't think there's a lot to be gained by like machine learning that or applying AI there without making a significant change to the way we approach the problem, which I think needs to be done in the longer term. Yeah.
Single-threaded tasks compared to the multi-threaded tasks.
How much of the time is spent single-threaded versus multi-threaded? It varies, and that's one of the things that we'll look for on our big designs, or rather a very related thing. So what we will often see, very much so on our biggest designs, but even on some of our sub pieces, our hierarchical blocks. One of the important pieces of this analysis is that we need to provide some sort of constraints into the design. We need to say, well, my clocks are running at 1 gigahertz. That's getting to be kind of old. My clocks are running at 2 gigahertz. And I have some paths that are special. I need to give them 2 cycles of time to get where they need to go. Here's some things that don't ever switch. I'll call those false paths. And I'll code some constraints and some exceptions. And so we write that in a scripting language called Tickle. And the most efficient thing would be for everything that constraint language needs to do, everything to be hard-coded. And that may be, if I had to put in every exact name in the design, that may be thousands of lines of tedious code to maintain. So I'm going to do some pattern matching things, and I'm going to maybe some for loops, various different things in this scripting language. And all of this constraint language, as general, maybe under the covers there's some threading that helps it, but it's generally single-threaded. And not just this single-threaded piece is significant, but what we run into sometimes as well is now I've done a pattern match where I said, give me all of the things in the design that match XYZ. And so my tool has to go look at 1 billion object names and return the ones that match XYZ. And so if I have 1,000 pattern matches in my script, and I need to do 1,000 pattern matches on 1 billion objects each, well, that starts to show up as a significant piece of the runtime. And so now That's an additional thing that I need to do to be able to scale up to my big designs. Maybe I'll run my script once, write the flat expanded translation of that script out as a new script, which is now harder to maintain, but much quicker because it has the exact names instead of having to do all those pattern matches. So now I have more work to do to try to address that single-threaded pattern match part of the tool flow. Other questions? These are good. I appreciate all the questions here.
Regarding the case where you had the master having downtime when the clients were running, what's preventing there from being a client instance running on the master device and having an assigned work to itself?
Yeah, I'll jump back to that slide. So almost there, I think. So in this chart where the master is idle, why doesn't the master do some work? I think there's two answers there. One is probably simplicity of the architecture and not making the master into this weird half master, half client thing. I'm sure that's a part of it. The other part here is the data model. So let's say the master needs to load every object in the design, all billion objects that I have in this design, and have some pieces of data associated with that. It's going to have connectivity, so it knows A is connected to B. It's going to know what type of cell, what type of inverter, buffer, AND gate, OR gate, what those are, but a small data structure. And then the clients are going to have more information. They're going to have what is the transition rate of the signal coming into that block, the transition rate of the signal going out of the block, what time did it arrive, what time did it get out of the output, what was the, well, maybe the master also has information about capacitance loads. Clients are going to have information about the capacitance and resistance. So the clients each need a bigger data model to do what they're doing, and the master can make do with a smaller data model for each object. That becomes important because for the master to have the full design, what we see is the master's typically around 1 to 2 terabytes of data. And those are my, I mean, every generation, memory prices are not coming down as much as we'd like them to. They came down, like I said, about 80% over the past 15 years, but still, that master on a 1 to 2 terabyte machine, that's my more expensive machine, so I guess I wouldn't like it to be idle. But if I'm doing client type tasks where I need more data, now I'm going to start raising the footprint of that master task. And I want to do everything I can to keep him reined in and not using any more memory than is possible. So that I think that's the main restriction on the master.
From a CPU perspective, can the master task have quite a bit less CPU or GPU resources than the clients as a result?
I think, can the master have less CPU? Yes, I think the master is less affected. Well, there's two things, and I think they're kind of illustrated here in the chart. Overall, if you look at the full, all the red and the gray here, master has 4, 5, 6, 7 boxes out of however many, I don't know, I'll make up a number and say it's 7 time units out of 30 time units. So the master is a smaller piece of your runtime. Maybe it's not that big of a deal if he has a lot of threads or if it's a fast processor. But every time that we're waiting on the master, all the clients are now sitting idle. So It's really in my interest for the master to be as fast as possible, so I'm not wasting the valuable client time doing nothing. Yeah, good question. Other questions out there? All right, I'm going to put my son on the spot here. Miles, do you feel like you know just ever so slightly more about what I do? No? Maybe a little bit more about what I do. All right. Good, good. All right.
If there's no more questions, I think we'll end it there. Thank you, Tim. Thank you for everybody.
Were you sneaking in a question?
Oh, okay. Yes, if you could please sign in, that helps us with our attendance records and for our reporting. So, thank you.
That was fun. Thank you for all the great questions.
Yes, thank you very much. And just one more announcement. We do intend to have a meeting in April and one in May before, taking a little more time off in the summer. So just watch for those notices to come out. Thank you.